will tell us about dispersion interaction in exciton-localized states. Thanks.
Yes. Hello, can you hear me?
Yeah, yeah.
Yes, and I guess you can see the title. It's my pleasure to join you remotely from Warsaw and share with you some of the results of our latest research on dispersion interactions involving excited states. So contrary to Anthony's talk, this will be more of a method development talk rather than a software development, but we'll also find some overlaps here. Just a brief introduction. As you all know, non-covalent interactions involving excited states are of crucial importance for our understanding of charge and energy transfer processes between molecules. So we would like to be able to model them quantitatively so we can design new materials with longer lifetimes and higher quantum yields. So for instance, the spin fission process depicted here is expected to be driven by non-covalent interactions, and its understanding could give us in the end more efficient solar cells. Another aspects, of course, are the so-called solvatochromic effects. So the way in which the interaction of between the solvent and the solute changes the absorption and emission spectra. Of course, these interactions involving excited states are not only interesting and fascinating to model, but they are also way more difficult than ground state interactions. And ideally, we would like to have some black box multi-reference method, which is also efficient. But as you all know, this is not the case. In reality, we have to deal with many problems such as size inconsistency on intruder states. If we limit ourselves to singly excited states, then we can usually get away with some accurate linear response models, such as CC2 or CC3. These, however, quickly run out of steam for larger systems. They become too expensive. And on the ab initio side, we are often left with a time-dependent DFT, which of course has many limitations. And from the perspective of non-covalent interactions, one such major limitation is that most of the existing dispersion corrections have been designed and parameterized for ground states. So they are bound to fail as soon as we deal with some excited states, which are very different from the ground state. And our motivation here was to focus on a particular aspect of these interactions, namely on the ability to calculate London dispersion for complexes involving excited states. So once we can do it, we can actually combine it with other energy components in the perturbation series, or we can supplement some supermolecular calculations with the missing dispersion. And here I will just show you some examples that we've looked at for low-lying pi star and n-pi star states. And to be more specific, I will only focus on systems with localized excitons, as the title suggested. And this is because simply in order to treat excimers, we would need a degenerate perturbation theory, and we are not there yet. So just a brief look at the theory behind all of this. So let us consider a dimer which dissociates into molecule A in electronic state I and molecule B in electronic state J. And as I mentioned, the unperturbed problem is non-degenerate. And the dispersion energy, as is well known, can be expressed through transition energies and transition densities of the monomers for such a dimer. And actually for excited states, we can divide this formula into several contributions that I will denote as W here. So let's take a look at them. But the first one, the first contribution will just involve excitations from our reference state to higher lying states. So this is, of course, the only contributions that we have when we consider ground states. But when we deal with excited states, we also have to consider those de-excitations. So other terms in which we go from our reference states to all of the lower lying states. And in particular, the second term here, this describes the situation in which we have two exciton localized on two different monomers. And this term is always positive. So this will shift our dispersion energy to positive values. And of course, it's quite easy to write down such a formula, and it's well known. The real question is how to actually calculate it. And this we will do in the framework of a method that we've been developing for some time. This is a multi-configurational variant of the symmetry-adapted perturbation theory, which we just abbreviate as SAPT-MC. And in SAPT-MC, we get the access to the necessary quantities, so the transition energies and transition density matrices, by solving extended random phase approximation equations. These were introduced by Katarzyna Pernal back in 2012. The nice feature of using extended RPA is that the only input that we need from the wave function, from the multi-configurational wave functions, are those 1 and 2 RDMs. So in other words, SAPT-MC can be applied with any MC wave functions for which we can generate 1 and 2 RDMs. And here I will just show you results for CAS-SCF, but we can also do it DMRG, as Anthony mentioned. We can do it with SIPC, GVP, and so on. Okay, so for those of you who are not so familiar with SAPT, this is a method which allows for a direct calculation of interaction energy as a sum of well-defined energy contributions. In SAPT-MC, we usually include only contributions up to the second order in the intermolecular interaction operator. That means we sum up the electrostatic exchange and the second order induction and dispersion interactions. And I should also mention that this method has been coded and implemented in a Gamcork package. This is a small code that we started to develop, and this is interfaced with the Trex.io library. So in principle, this can be interfaced with any code which gives us 1 and 2 RDMs. Okay, so let's go back to the formula and ask ourselves, well, are these the excitation terms, can they really be relevant, and do we really need to care about them? So this is just an illustration, a simple system. This is argon atom interacting with ethylene. As you can see, the complex is kept in a C2V geometry, and we vary the distance between the atom and the center of mass of ethylene. So on the left, we are looking at the ground state. This is just the interaction energy curve. And here, everything works perfectly. So the red curve here, this is our SAPT based on CAS-SCF reference. And this overlaps coupled cluster results and matches it very, very well. What about the right side? Well, this is the argon interacting with pi star state of ethylene. And now the red curve is SAPT based on CAS without those red terms. So we exclude these de-excitation terms. So as you can see, we are missing quite a lot with respect to reference. We can do some other thing. We can simply take supermolecular CAS-SCF and add dispersion energy on top of it. But this still is pretty far away. So what about if we include those red terms? So these here they are excluded, and then we include them. As you can see, these can be really relevant, and in this case, now we have a very, very good match with a reference coupled cluster curve. And so in this case, this was almost 20% of the total dispersion. Right, so for this study, we have looked at some more interesting systems, which we selected from the S66 dataset of non-covalently bound dimers. So these will be benzene, pyridine, and some simple peptide interacting with water, methanol, and methylamine. As I mentioned, pi star and pi star states. And let us start with looking at the energy decomposition and seeing, well, what we can learn from SAPT about these complexes. Okay, so let's start with benzene complexes. These will be all, of course, the exciton is localized on benzene in all 3 cases. And all of these complexes are actually similar. So we can use the ratio of the dispersion energy to the electrostatic energy to sort of assign this complex as a mixed. So this is not, both of these terms matter. But what we can see is that when we compare the ground and excited state, these values become higher in excited states, which means, of course, that dispersion becomes more important in excited state. The other thing that we immediately see is that, well, compared to the ground state, all of the magnitude of these components is diminished in excited state. So we'll look into that in more details in a second. Just last thing here is to look at these de-excitation terms that I mentioned. Well, here they are well below 0.1 kcal per mole. So they are not really relevant, but we can calculate them and see if they are contribute or not. So this is a more detailed look. Here we will look at the interaction energy differences between the excited state and the ground state. So these will be different SAPT components, right, contributions. And minus in this table will correspond to stabilization of the excited state, and plus will, of course, correspond to excited state being destabilized. So let's add some colors. So indeed, as we suspected before, the excited state is destabilized. And the main contributing factor to that is the change in the electrostatic energy. But actually, by doing all the composition, all the subterms, we see that, well, this effect is largely cancelled by the first order exchange. And we actually need to go further. And in particular, we need to also account for the destabilization coming from the change in the dispersion interaction. So these are, I would say, non-negligible, and this is it's good that we can calculate them now. The second example are typical hydrogen bonded complexes. So this is peptide with water and methylamine. This time, this is not pi star, but n-pi star. So this will behave differently. Yes, and this is again this dispersion to electrostatic ratio. This just shows us that this is a typical hydrogen bonding situation. And as we might expect, the dispersion energy does not really change upon the n-pi star excitation, but the redistribution of the electron density affects the electrostatic component. So we might have guessed that, but now we have some numbers to actually verify it and quantify it. Though the excitation energies, well, since there's a very little change, they are basically zero. And here's just to see this in more details. So as we expect, the main contributor is really this change in electrostatic. The effect from first order exchanges is very small. We have actually some non-vanishing exchange induction terms in this case. So this confirms that, and this has actually been shown in previous studies which tried to perform some energy decompositions, but not without dispersion, that the main effect it comes from electrostatic for these complexes. And the last group, these will be two complexes, which are again hydrogen bonded ones, but this time we will look at pi star excitations and the one which is of a mixed character. So again, we see we can verify their character, but also again, what we would expect, well, that the pi star excitation will not really affect the electron density around the nitrogen atom. So actually, the electrostatic does not really change between, for the first two complexes, it does not really change between the ground and excited state, and there is some change in dispersion. The excitation terms, they start to approach 0.1 kcal. So we can say that they start to contribute. What about all of the terms? Again, well, the only real difference between ground and excited state in this case is observed for the mixed complex, as one might have guessed. But actually, we see that the destabilization from electrostatic is basically almost entirely counteracted by the change in first order exchange. So we really need to be able to calculate dispersion to see to get this final destabilization for this complex. The last thing that I wanted to show is you might ask, well, how accurate are these numbers? We perform some decomposition on pretty small effects, right, in terms of kcal per mole. So this is just to show you errors, mean absolute percent errors in total interaction energies for ground and excited states. So the green bar here, this is just supermolecular Cas-SCF. And this, again, is not a surprise. This underestimates the interaction energy and gives percent errors around 90%. The simple addition of dispersion actually gives a much better result. So this is somehow fortuitous, and there is, of course, some error cancellation, but actually Cas supplemented with dispersion is already a pretty decent effect, a decent result in terms of interaction energies, and actually performs better than Cas-PT2. And our SAPT in both cases, so for both ground and excited states, SAPT values and errors are below 5%. And this, I believe, is a good indicator that the energy decomposition that we do actually makes sense and allows for some physical interpretation. All right, so this is just to conclude. I have shown you that, well, leaving out many details, but I have shown you that we are now able to calculate the second order dispersion energy for excited states with localized excitons, and this can be done in the framework of the multi-configurational SAPT. And I have also shown you for some simple model systems that this decomposition is pretty useful to interpret the change in the binding patterns for these low-lying excited states. And well, hopefully, I have convinced you that, well, actually one needs to care about the dispersion effects if one wants to stay on the quantitative side of things. So all of these results and much more have been recently published in a JCTC paper, and the GAMCore code is open, can be downloaded. And so let me finish with thanking many contributors, people who actually did the job, and in particular to Professor Katarzyna Pernal, with whom I enjoyed my postdoc stay, and we've worked on SAPT-MC and many other projects, and also the TREX and National Science Center in Poland for funding. And of course, you for your kind attention.
Thanks. Are there any questions from the audience? No? Nothing on the Zoom chat. So you mentioned something about degenerate perturbation theory. Yes. Are you working on extending the code?
Oh, yes. I actually got a grant for degenerate SAPT. So this is something that I will now work on. Yes.
Okay. Thanks. So if there are no more questions, let's thank the speaker again.